Okay, here's where we left off when we were trying to find out how many combinations of 5 cards can be drawn from a 52 card deck. We had come up with this formula that the combinations would be 52 factorial over 5 factorial times 47 factorial. In general, we can change this formula. Well, let's first of all figure out how we could compute this by hand, and then we'll give the general formula. So if I wanted to compute this by hand, I could start writing out 52 factorial, but I don't want to write 52 all the way down to 1. I can write 52 times 51 times 50 times 49 times 48 times 47. I can stop there and put a factorial after the 47 because you'll note the denominator has a 47 factorial. Now, the denominator also has a 5 factorial. I do want to expand that into 5 times 4 times 3 times 2 times 1. So that's 5 factorial written out. Okay, so we didn't need to write out the 47 factorial. So computing these by hand is not too bad as long as one of the factorials in the denominator is almost as big as the numerator factorial. And then you can look at what's left and you can simplify. Okay, so I see I have a 5 and a 50. So I can make that a 10 and I can make the 5 a 1, right? And then I have a 4. Well, 4 would go into 48 very nicely. So I could take 4 and 48 and make that a 12. And then, I have a 3 and a 2. Let's work on that 12. The 3 and the 2 are 6. So that could become, the 12 could become a 2. And so I would be left saying that this is the same as 52 times 51 times 10 times 49 times 2. And I can pretty quickly put that into my calculator. In fact, let me just do that right away. So if I were doing this by hand, it wouldn't be too, it would take a little while to multiply all of these numbers, but not too long. With a simple calculator that simply does multiplication, addition, subtraction, and division, I could compute it pretty quickly as well. But if I had a calculator that did factorials, I would just use those. Now, this is a very large number. It's 2,598,960. Okay, so there are well over 2.5 million ways that I could be handed 5 cards from a deck of playing cards, or 2,500,000, which would be 2.5 million combinations of cards that I could get. In other words, different hands where the order doesn't matter. So that is a smaller number than if we had just looked at the permutations, because then we wouldn't divide by the 5 factorial. So it would be a lot larger number if the order of those 5 cards mattered. But you can still see this as a lot of possible hands that could be dealt when you're handed 5 cards from a deck of cards, which is why games like poker are very interesting. So let's, certainly from a probabilistic standpoint. So that's what would happen if you drew 5 cards. Let's consider what would happen if we drew even more cards. So, and let's first go to the general formula. So if in general, I want to find the combinations for n objects taken r at a time, n equals the number of objects, or I was calling them members or elements. Let me just say number of objects in the set, but objects in quote, because it could be something other than an object. Could be people. They don't like to be called objects. R is the number selected. And it's almost like the permutation formula. It is n factorial, and we have an n minus r factorial, but we also had the r factorial. So we need to divide by the number of ways to organize the set that is selected as well, since the order doesn't matter. I'm going to divide that out. Okay, so we just attained an answer for 52 objects drawn 5 at a time. Let's find out the combination for a few others. Let's find the combinations for these. And we'll talk about how to do these on your calculator. to save time. Let's do 5210. That would be actually much harder to do by hand because we would have 52 factorial over, let's see, there would be 42 that weren't picked and 10 that were. And so we'd have to go a lot longer down the number of factors in the numerator before we got to 42 factorial. So we would have a lot more left over. So simplifying that would be harder, and there would be a lot more to multiply out if we didn't have a calculator. So fortunately, we don't have to put all of this in the calculator. We don't even need to use factorials. All you need to do is go back to math. You could put in the number 52 first, and then go over to the probability menu, and then go down until you get to combinations. And let me see how many we have to go down. So if I hit math, go over to probability, you should be doing this at the same time that I am. Math, go over to probability, do not hit enter like I just did because you'll just pick a random number. You can see that it's the third option down. So if you arrow down twice, you'll be to NCR. And if you hit enter, there will be little boxes where you can enter those things. Okay, so in the first little box, so you'll see something on the screen with two little boxes. In the first little box, you'd want to put the number 52. And in the second little box, you'd want to put the number 10 and get your answer from that. I'll pause the video for a second. Why don't you try to do that? Okay, the number of combinations went up drastically. In fact, it's so big that you wouldn't want to write the ones place for this. Right? The answer ends up being 1.58. I'll just copy that many digits times 10 to the 10th. All right. So remember, 10 to the 9 equals 1 billion. So 10 to the 10th is 10 billion. So this is really close to 16 billion. It would be, if we move a decimal point, we have about 16 billion ways that we could get hands of 10 cards. Now, again, remember the order of those cards wouldn't matter. It's just what combination or group of cards that I have, and then I could reorder them in my hand if I want to, because the order is irrelevant. It's just the group that I pick. So there's 16 billion ways I could do that. Now, there aren't too many games where you actually are dealt 10 cards originally, but if you were, you would be able to have 16 billion different ways to get those 10 cards. Now you can see that went up drastically. Let's see what would happen if we went to maybe a hand of 25 cards. So if we did 52, 25. Go ahead and practice putting that in your calculator while I compute it on mine. Okay, so you can pause the video if you need to compute it. But when I computed it, I'm about to write the answer. Once again, I'm going to round this because the number is so large. I got about 4.8 times 10 to the 14th. All right, so 10 to the 12, let me write this over in red. 10 to the 12 would be a trillion. So 10 to the 14th is 100 trillion. All right, so this is about actually close to 500. The number I have here is close to 500 trillion ways that we could do that, right? Now, I don't know of any games where you'd be handed 25 cards. It would be pretty hard to hold those 25 cards in your hand. Although maybe the game of war, where you actually divide the deck in half, you end up with this. Now, in the game of war, the order of your cards matters. So you might want to actually look at the permutations for that. And it would be ludicrously large if you were to be doing that. All right. Moving along, though, these numbers keep getting bigger and bigger and bigger. But you can see right here, we're near the point of giving out half of the deck. What would happen if we kept on going and instead of giving out half the deck, let's do the reverse of what we did in this example right here. Instead of giving out 10 cards, let's give out all but 10 cards. So let's look at the combinations of 42 cards drawn from a 52 card deck. Okay, so you could put this into your calculator, be the combination for 52 comma 42. So that would be the combination of 52 things with 42 selected. And you would see that it is 52 factorial over 42 factorial 10 factorial. All right, that's what it would be equivalent to. And if you either use the factorials or you do it out, okay, it turns out the number is about 1.58 times 10 to the 10th again, right? The reason why is because if I do the combination of 52 comma 10, there are 52 factorial ways to shuffle the deck. The cards that are selected could have been arranged 10 factorial ways, and the cards that weren't selected could have been arranged 42 factorial ways, and it's pretty easy to see that these will end up giving you the same answer. So as we get past the halfway point in giving out the cards, the number of combinations actually drops. In fact, you can think of how many ways could you hand out the whole deck? Think about that for a second. And the answer is 52 factorial over 52 factorial, 0 factorial. And remember, 0 factorial is 1. So this whole result would be 1 because there's only one way you could hand out the whole deck. If we're not worried about the order, somebody would be left holding all 52 cards in their hand and they could order them however they wish in their hand. So by the time we get to a combination of 52 things with 52 selected, we're down to just one possibility again. Okay, so I think that's how you calculate combinations. You'll see some of those in your homework. There are a couple tricky homework problems though, so we want to go over some ideas where there are hybrids of ideas put together in order to solve a problem. So we'll do that in the last video.